Okay, so good evening, everyone. This is Krishna Chanavtar, and I will be holding the fourth tutorial session for this NPTEL course on foundations of wavelets and multi-rate digital signal processing. So in today's session, we would be covering some of the aspects of the week 4 of this course, right? So that is the plan, and of course, we'll be demonstrating some of the aspects of wavelet analysis using MATLAB and I'll be, as usual, I'll be doing some of the tutorials that are available online, so that it's easy to follow. And if possible, I'll also try to start something about PyWavelets package. Okay, so let's begin with week 4 of this course. So in the last session, we had discussed about the synthesis and about filter banks in general. And we had talked about the Haar filter bank, which is the most fundamental banks, right? And we had also discussed about how do we say decompose a signal into its in terms of the representation in the scaling function basis and also in the wavelet basis. So continuing the discussion further, we would be today we would be analyzing some of the this analysis of Haar in the frequency domain corresponding to the filter bank. So that is the aim as of now. So at first, so the goal is like say we have this essentially. Let me just summarize what Haar analysis. Right. So essentially, we have a signal xn, which happens to be, just a minute, I'll mute from here. Fine. Okay, so we have a signal xn, right? And we pass it to two classes of filter banks, one which uh, uses it for doing that representing in terms of the analysis, which is expressed using this scaling function basis, and the other part is for capturing the disturbances or the variations about certain mean, right? And we then downsample it, or what we call it, we decimate the signal. So this is the part for the analysis part, right? And how about synthesizing the signal back? So we have the signal xn. Of course, once we have, say, done the decomposition part, then we try to upscale the signal and have this analysis. The synthesis part, we have 1 plus Z inverse and 1 minus Z inverse. However, in this case, we have certain ambiguity with respect to where should we start. Should we add the 1 minus Z inverse component one step before or after that of the 1 plus Z minus 1 component, right? And then we just pass it through some header, right? We just add them up, and this is what gives us our signal. So we retrieve some signal, maybe xint, right? So there are the two components of this. Right? Now what we would do is Let's try to analyze this signal in the frequency domain. For the filter bank. So we have the signal as usual. We do some Z transform of this discrete signal, and the expression goes as xn e to the power, sorry, it's j to the power minus n. And we substitute it, z is equal to e to the power j omega. And we do this for a very reason that we want it to lie in the complex argand plane of unit circle. Right? So, and the requirement is that Z is an element of R, which is the region of convergence, which is the script R it is. It's the region of convergence. Now, typically, R is between two circles centered at Z is equal to 0. Right? And this simply says that this is in general, that's how we want it to have the region of convergence to lie in, right? So say we have this circle here centered at origin. So something like this, this circle, another circle. The inner circle is of radius R1, and the outer one is of radius R2, right? And then what we do is R1 could be 0, and R2 could be infinity, right? And the boundary circles may be included or excluded. Yeah. So that is, and in particular, if we look at a unit circle, then the unit circle, of course, lies in this particular region of convergence, right? And say if we have this Z transform of a sequence, then it implies that even the sequence will have a discrete time Fourier transform. Essentially, this part of substituting Z is equal to the power j omega is itself uh, bringing our system, the Z transform, and converting into what we call as the discrete time frequency, discrete time Fourier transform of the sequence. Now, suppose, say we have, we were talking about these classes of analysis filters, right? So there are two classes of analysis filters. And we had this one part, the first one was 1 plus Z inverse divided by 2. And the second one was 1 minus Z inverse divided by 2. So these are mean and this the disturbance, right, of between two successive elements in the sequence. Now suppose we say choose the first, let's begin with the first analysis filter, and then say right, and then we have 1 plus e to the power minus j omega by 2. And this is equal to e to the power minus, right? We've substituted this, and then what we do is we want to uh, convert into some sort of a sines and cosines form. Right. So one way we can do is, as has been done in the class, was to assume the way it was done. Or the other way could have been just say you have 1 plus e to the power minus j omega. From the Euler's formula, you have cos omega minus j sine omega and divide by 2. Of course, this is going to be a long route, so I believe that's the reason why it has been done the other way. And you have 1 plus cosine omega is also can be written as 2 cosine square omega by 2. Likewise, minus you have j, and sine omega is 2 sine omega by 2 cosine omega by 2 whole divided by 2. And what we see is 2 cancels out, and we have cosine omega 2 as common, right? And this, then we have cosine omega by 2 minus j of sine omega by 2. And this can be written as cosine omega by 2 into e to the power minus j omega by 2. Right? And this is what we had seen in the lecture. So what we have here is that the magnitude is equal to of this is cosine omega by 2 into e to the power minus j. And this is going to be equal to modulus of cos omega by 2 into the modulus of e to the power minus j omega by 2. This comes out to be, and the modulus of e to the power minus j omega by 2 is 1. So effectively we have right. And this was about magnitude. And what about phase, right? So we are also talked about phase. So the phase is let's start the expression again. So 1 plus z inverse by 2 is essentially, I can just put it like this as well, to cos omega by 2, right? So phase essentially, now when you look at the, when we had broken into two parts, right? So you have cos omega by 2 minus j sine omega by 2 in its using this Euler's formula, and you have cos omega by 2. Now it's, and as we see that cosine omega 2 multiplies both the real and the imaginary parts of this expression. And the way we define phase, so phase is essentially angle, right? So angle is will be equal to so at first we can have something called as a tan angle, right? And tan is given by the imaginary part divided by real part. And the imaginary part is going to be minus sine omega by 2 into cosine omega by 2 divided by real part is going to be cosine omega by 2, of course, again cosine omega by 2. And what you see is cosine omega 2 cancels out. However, there is a requirement that the omega by 2 uh, must not be equal to pi by 2. For then only you can cancel it. Otherwise, it becomes 0 by 0 form, right? So this is the requirement here. So which means that, so say we have cancelled it out, then we have minus tan omega by 2. And when you take a look at this, and since we have uh, say bonded or bond omega on both sides by plus minus omega and plus omega. So in this range, what you can have is tan of this angle can be written as tan of minus omega by 2. And this implies that angle is equal to, you can just cancel out tan. Of course, that's like tan inverse of tan. And within this range of omega, it will just be minus omega by 2. And this is what we call as the phase of the angle, right? Or phase of this frequency response. Now, say you have this magnitude was magnitude response was partial cosine omega by 2. Angle was minus omega by 2, right? So and cosine omega by 2, the absolute value is going to be at 0 and say pi bounded on both sides by pi minus pi. So here is going to be 0, drops down, it becomes pi by 2, right? So you have cosine of pi by 2 is 0, and similarly cosine of also 0. So this is the maximum value, and this is essentially what you have here, cosine omega by 2, right? And the angle is the phase angle varies in this manner. You have pi, you have minus pi, 0, and it at when when omega is equal to minus pi, then minus into minus gives us plus. So it becomes here it's minus pi by 2 for at omega is equal to minus pi, gradually decreases and reaches its lowermost value of minus pi by minus pi by 2. So here you have it reaches a minimum value of minus pi by 2, and here it's plus pi by 2. So you can see that it is linear, right? The phase is linear, and there is the reason that we call such filters where phase is linear to be a linear filter, right? In terms of phase, right? So which means it's linear phase, right? Okay, and you may be quite aware that if we pass a signal through a filter, right? Say we have this signal here. So you have this filter here, and say in a continuous time filter, we have a signal which enters at A naught cosine omega naught t plus phi naught and you have this frequency response. Now, any such filter in frequencies in frequency domain, it's represented in terms of its transfer function. So h omega, right? However, at omega is equal to omega naught, we have h will correspond to it will act on omega naught, right? So the signal, what it will be done is it will be multiplied by h of omega naught into a naught cosine omega naught t plus phi naught. Now it seems that h of omega naught is a complex number in general. So it will always it will be written in the following manner. Here the magnitude e to the power minus j some angle, that minus of angle say h omega naught. Depends on how do you like it, say that it can be plus or minus, but say some angle it has, right? I'll just call it plus minus some j angle. So once you do this, you have to just substitute in the output signal, and it will be having h of omega naught and e to the power this, right? So it will all it will do is it will try to change the phase. So let me call this angle as h of omega naught, since this angle will also be a function of omega naught, right? So plus t plus phi naught plus angle of h omega naught. Now you can rearrange these things, these entities in this equation, and call it angle of h omega naught divided by omega naught into omega naught. This is just some mathematical jugglery to state that what we have here is magnitude of h omega naught a naught. We put this with cosine here. So cosine and then omega naught t plus angle of h omega naught divided by omega naught plus phi naught. So what we essentially did was, what we did here was to change or bring a shift. So there is a shift in along the time axis, shift in t. And now let's look at this angle h of omega naught divided by omega naught. Now, if this ratio happens to be constant, some tau naught, then we call this to be linear phase. If this is the case, then it is linear phase. And we can call it, say, omega naught into t is given by so it will be so what we are doing is this angle of h omega naught is going to be tau naught omega. Okay? And this is the thing what we call as the linear phase. Okay? And the good thing or the most important example of this is the most important. I mean, the major advantage of this is it changes the phase linearly, and that is very useful to us, right? So it makes the computation much simpler. Now, for an ideal phase, also for an ideal filter, we would require for an ideal filter. We require angle of h omega naught to be 0, which is of course not possible in practicality. It's not. It's possible in the sense that it's not. I mean, it's not simply possible. Of course, you can recreate it using lot many systems, but um, simply it's not possible. Then the second analysis filter that we had was number 2, 1 minus z inverse by 2. Again, and of course we can repeat all those processes and say let's repeat it just for the sake here. So it will be 2 sine square omega by 2 plus j 2 sine omega by 2 cosine omega by 2 sine omega by 2 will be common, and then you have sine omega by 2 plus j cosine omega by 2. Now, this expression here, the complex part within parenthesis, the entire expression within parenthesis doesn't exactly match what we would expect for the direct application of the Euler's expression, right? So what we would do is, say we take j outside of this parenthesis. So we have j sine omega by 2. And you recall that j square is -1 and minus j square is +1. So effectively we can write it as minus j sine omega by 2 plus cosine omega by 2. And now you see it, we can utilize that Euler's formula in the sense that you have cosine omega by 2 minus 0 sine omega by 2. And you have e to the power minus 0 omega by 2. Now again take the magnitude. So the magnitude response would be right. So this is how it will look like. And how about the response? I mean, the phase angle or phase say. So it's going to be angle. Again, we can rewrite this entire thing. So what you have is, we can always refer back to this expression here. And we know that tan of angle is going to be equal to the imaginary part, which is cosine omega by 2 into sine omega by 2 divided by sine omega by 2 into sine omega by 2. And we recall that for it to be cancelled, to be able to cancel sine omega by 2 on the numerator and denominator, we would not want it to be something of the form of 0 by 0. So that is the reason we preemptively remove that part by saying that omega by 2 is not equal to 0. And this is the reason which you'll know later is why there is a discontinuity at omega is equal to 0 in the phase, right? So what you have here is, this is going to be equal to cosine omega by 2 divided by sine omega by 2, right? And with this, what we have is, so we have tan angle is equal to cosine omega by 2 divided by sine omega by 2. And this is essentially cot omega by 2. And from the from this trigonometric identities, we can write this as tan of pi by 2 minus omega by 2. And for the range that we have considered of omega lying in the interval minus pi to pi, you will have, you can simply cancel out tan on both sides and you have tan is equal to. So this is our phase. Let's plot the magnitude versus the phase. So magnitude of this will look like it's absolute value of sine pi by 2, right? So, so it goes from plus pi, it's plus pi minus pi here. And we always take this maximum, I mean, the absolute value. So sine of minus pi by 2 is going to is equal to -1, but the absolute value is going to be 0. So it's something of this sort. And you see that even in the magnitude, so this is going to be sine omega, magnitude of sine omega 2. There is a discontinuity, there is some sort of although it's continuous, it's not differentiable at 0. At omega is equal to 0, right? It's not differentiable. And for the phase, as we know, is that this angle is only, this operation is only valid for when omega lies from 0 to pi. And in this case, you have it goes from here and somewhere here is 0, set pi. And this expression, however, for omega lying between 0 to pi, you will have to slightly modify it. So angle, tan of angle, this one is going to be equal to, it's going to be so it's cot, right? So it's cot here. So you can write it 1 by tan omega by 2, right? And when omega lies between minus pi to 0, then even tan is going to be negative. Right? Since tan is going to be negative, what we can do is, let's not do all these complications. Then in that case, tan of this is going to be equal to minus of, say, tan something like this. Let's just understand it. So cosine will going to be negative in this. So it will be minus. It's going to minus of tan of this. And this we can take it to the inside and we can have minus pi by 2 plus x. Yeah, I think this makes, therefore the angle is going to be equal to minus pi by 2 plus x, right? So it starts from here and ends at here. That x is equal to 0, it's going to minus pi by 2. And here it's going to be 0. Right? Here it's pi. And you see that there is a discontinuity, right? So there's a discontinuity in the phase at omega is equal to 0. Right, and taking a look at both these magnitude diagrams. So in this magnitude, it so happens that it tries to pass all the lower frequencies. However, towards the higher frequencies, it tries to attenuate the signal. So this can be, it somewhat tries to mimic, of course, not perfectly, but to certain degree of to certain degree, it's trying to mimic a low pass filter, right? So it allows some sort of a low pass to pass through through this filter. However, at higher signals, at higher frequencies, it tries to just attenuate the signal. And the reverse happens for the sine case, in which case you will have at higher frequency it tries to pass it through, but at lower frequencies it just attenuates the signal. Right? So that's the difference here in both the scenarios. And this we call as these are just quasi or pseudo linear phase, since it's piecewise linear, right? It is piecewise linear with a discontinuity at omega is equal to at zero frequency. Now let's look at certain important properties here. Say we have the first analysis filter, which was 1 plus Z inverse. And when we add the second analysis filter, 1 minus Z inverse, then it results in half 2 plus Z and plus Z inverse minus Z inverse. So it just cancels out. 2, 1. Right? And also when we look at the magnitude of these signals, magnitude response, then what we see is in the first filter, we have cosine omega by 2 as the magnitude, squared it, and then when you add it to the sines, they add up to 1. Right? So these are some of the features. So what we would, in general, what happens is uh, this property in general is called as magnitude complement. Magnitude complementarity. It's a property, and this is known as power complementarity. So it is as if these two filter banks that tend to divide or break down the signal or decompose the signal into two components, whose magnitude add up to 1, and who also preserves its power when combined, and the responses are combined from both of them. So in a generic way, we can call it to be, say you have H upper omega, which is the upper branch of any frequency response, and H lower omega, which is the lower branch, they add up to 1. This is the magnitude complementarity that we were talking about. And the other is we have H upper omega whole squared, H lower we just call it the power complementarity. Right? Now, and of course, we have already as discussed later in this week 4 of this course, there was a talk about what is an ideal filter bank. So ideal filter banks are what we would call as composed of two parts. So one is known as low pass filter, LPFID. So it's ideal low pass filter with cutoff at half, and the other one is the high pass filter with cutoff at half of at omega as at pi by 2 and pi, right? And you have a 0, and this is called as, of course, the magnitude is 1, and then HPF ID, ideal cases. So this is what we would expect from a signal, from an ideal filter bank. However, there are certain issues. The first issue is that why it's not possible, or why we cannot attain such filters, is they are non-causal. That is a very strong thing, right? In signal systems, or signal analysis, right? So, or any system, we must the system must be causal in nature. And what do you mean by causality? And it is a very fundamental but this is very fundamental to signal and to any systems, to any system in general. So causality implies that input leads to output. So, and this implies that the input must be given before, then well you can have output. So in the sense that epsilon is greater than 0. So it should happen like that. If the system does not uh, have this causality principle, then this is a very fundamental violation of what we call as the action reactions principle, right? So the output or the action must always follow, or in essence, the effect must always follow the cause, right? So it's essentially this is the cause and this is effect. So you cannot have an effect without a cause. So that is a fundamental assumption of any processes, right? And you'll ask, but why is the case? Say this, you have h of omega. Then let's try to determine the impulse response. And since we are dealing with a discrete signal, then what we can do is let's take this is the impulse response is, of course, the inverse or the inverse discrete time Fourier transform of a impulse response, right? Of its of the impulse response in frequency, or the impulse frequency response, right? So we'll have h of n. This is going to be given by minus pi to pi h of omega for the ideal case. So this is what we want as the ideal, right? Ideal omega and e to the power j omega n and d omega. So far, so good. Now what we will do is we will have minus pi to pi. And what we see is that h of omega and this, right? So it's going h of this is always symmetric in nature. It's always symmetric. It's a symmetric function. So that's the reason we only drew half of that. So you can just divide it into it. I mean, you can just express it twice of the definite integral, definite, or the limits of the integration you have. You can have 0 to pi and then h of it omega e to the power j omega n d omega. Now we can move a step further. I mean, along these lines, and even break this down into two integrals. 0 to pi by 2 h ideal omega ejwn omega n d omega plus pi by 2 to pi h ideal omega e to the power I j omega n d omega. And h I omega is 1 in the interval 0 to pi by 2. And this is going to be 0 in this interval. So you are left with this 2 into 0 pi by 2 and e to the power j omega n d omega. Okay. Okay. So all that we can have is, let's expand it. So we can write it in terms of 2 and e to the power j omega n divided by omega n, since that is what the integration leads to, 0 to pi by 2. That's 2 into e to the power j omega. So it is like pi by 2n minus to the power I into 0 divided by omega n. Right? And this you can write it as, of course, the way you see it. Of course, we will require a new slide for this. So we'll have E is equal to 2 into e to the power j pi by 2n minus e to j into 0 divided by 2, 0 divided by, what was that? Okay. This comes out to be, I think it's not the omega and it's not coming, right? It's j into n. Yeah, sorry. Divided by j into n. And this is this goes out to be So we should write it as cosine pi by 2 n plus j sine pi by 2 n minus j into 0 e to the power 0, right, is just 1. So this h has to be just 1. This is going to be equal to, so this, since the signal is real, right, so we have to have the real part. So you have cosine pi by 2 by n of let me look so the scenario here. J omega n divided by, so it have this from 0 to half. One Jn Let's start from the scratch. I believe we have it's leading us to certain complications here by taking just one part of the integral. And despite knowing that it's true, but we want it to be, we just completely integrated our one part. So see, this is what should look like. See, we start from scratch here. I mean, so far so good. We don't introduce the symmetricity in this problem. So we can have this, write it down as it will only be non-zero for minus pi by 2 to pi by 2 e to the power j omega n d omega, and it results in, say, e to the power j omega n divided by jn from minus pi by 2 to pi by 2. And this leaves us with a very simple expression. It should give us 1 by jn e to the power j pi by 2n minus e to the power j pi by 2 minus j 2. Okay? And as you recall, you can write it as 2 by jn. It should also be 1 by 2 pi, right? So let's always have that in mind. 2 pi, right? So it becomes 1 by pi n, and then you have e to the power j pi by 2n minus divided by divided by 2j. And this is nothing but sine pi by 2n divided by. So I believe this was unnecessarily complicating things the way we chose it to be. And let's, of course, it should be identical because we are using, but it's introducing that the complex expressions. Now, how about that for a high pass filter? High pass filter, what is it? And here, what I wanted to note is that, so the H of LPF, the ideal LPF, and N is given by sine pi by 2n divided by pi n. And of course, what we assume is that h is not equal to 0. And if n is equal to 0, then we need to determine a limiting case. Limiting n tends to 0, then you have to use Laws-Pizel's rule, and then you have pi by 2 sine, pi by 2 cosine, pi by 2n divided by just pi. Pi cancels out, then you can just put n is equal to 0, and lo and behold, you have just half. So half is for n. How about h of a high pass filter? Is going to be 1 by 2 pi integral of minus pi to pi. Okay. And h ideal of omega e to the power minus j omega, sorry, e to the power j omega and d omega is going to be equal to, and this was for HPF, right? For corresponding to the high pass filter. So we have 1 by 2 pi, and this expression is going to be valid only for minus pi to say minus pi by 2. You will have this into this. This gives us in this we have h of the value of frequency response to be 1, j omega n d omega plus pi by 2 to pi. You have, so we use some mathematical trickery in the sense that you take some say lambda is equal to minus omega, then this implies that d lambda is equal to minus omega d omega. So even the limits should be negatives of each other. So you can have 1 by 2 pi minus this one. This one would become pi, right? And this becomes minus pi by this becomes pi by 2, right? And you have e to the power minus j lambda n d lambda, that also in negative form. So we are essentially making all these manipulations here, and this goes from pi by 2 to pi e to the power j omega n d omega. And this here simply becomes 1 by 2 pi. And recall that minus of some definite integral becomes just you change the limit, the order of limits. So you can write it as pi by 2 to pi and e to the power minus j lambda n d lambda plus the rest. And you know that lambda is a dummy variable, so you can still just write it as pi by 2 to pi and e to the power minus j, just substitute with omega n. So you have d omega again. And likewise, you have pi by 2 to pi e to the power j plus j omega n d omega. Now what you can do is you can bring both these terms into one single integral from pi by 2 to pi. And you have e to the power minus j omega n plus e to the power to power j omega n divided by just have this, right? And you know that yes, adding it up gives us cosine 2 pi, cosine pi wn, right? So you have 1 by n, so pi by 2 pi, and this gives us cosine uh, just omega n d omega. And the rest of things is as straightforward as anything else. Yeah, 1 by pi by 2 to pi cosine omega n d omega, and the integral of cosine is sine, so it was 1 by pi sine omega n divided by omega. We will divide by n and the limits from pi by 2 to pi. So what we have with is 1 by pi n sine pi of n minus sine pi by 2n. And that's what it is. Now, this will have some special cases. So what about at n is equal to 0? At n is equal to 0, then this term is, so this was HPF. At n is equal to 0, it so happens that you have HPFN, HPF, the ideal version is equal to, so it's 0 minus 0 by 0, right? So you'll have that limiting case L tends to infinite, L tends to 0, N tends to 0, and you'll use that what we just some time back learned as the Lorentz-Pitzels rule. It will be pi of cosine pi n minus pi by 2 cosine pi by 2n divided by just pi. Now we can substitute n is equal to 0, so it will be pi into cosine pi into n is just minus 1 minus pi by 2, and then So n is equal to 0, right? So it is going to pi into cosine of 0. So it's 1 minus pi by 2, and cosine of 0 again is 1. So what we are left with is pi by 2 by pi is equal to half. Right, so it's half. Right, so this is the scenario here. And what you need is the reason for it being non-causal is that even if you have, say, uh, so impulse response is always, say, you know that impulse response is when you have un, the provider, the input, but h of n seems to depend on all n. So un, the impulse response starts at, say, for example, you have the impulse will start at this, right? So it will be at n is equal to 0. However, h has a value all across. So it's non-zero everywhere. So it means that there is signal, there is output even before input. That is the reason it is non-causal in nature. So that was one thing that we had wanted it to talk about. And the second thing is about the about the divergence of right. The second property was about divergence. The ideal filter is divergent. Okay, so the ideal filter is unstable. In the reason why, the reason is because the summation of h magnitude of the impulse response, h of n, right? Over all, the summation is divergent. And we can even look at from the graphs here, right? So we have, say, for the low pass filter, we had low pass filter LPF ideal. We had h of n is equal to sine of pi by 2 n divided by pi n, for n is not equal to 0, and half for n is equal to 0. So what you have is when you sum all of them, n, then n is equal to minus infinity to infinity, then what happens is, let's take the first half. So start from n is equal to 0. So you have plus half plus, and you put n is equal to n is equal to 1. Right? Then it becomes, it's like sine in of pi by 2 divided by pi, right? So it becomes 1 by pi. Likewise, when you put n is equal to 0, so n is equal to 2, then you have sine pi. So it becomes 0. However, for sin, when you put n is equal to 3, then it becomes 3 pi by 2, and the mode will be 1. So it will becomes 1 by 3 pi. Right? And this so happens that as you keep on increasing, it will be unbounded. Like this tends to plus infinity as it is of plus infinity, right? So that is the reason it diverges. as you keep on increasing n, you're actually adding more and more terms, and it somewhat mimics a series of 1 by n form, right? So in that sense, it very much mimics. So it's somewhat like 1 by n form, and you can actually see that it's of 1 by n form. So this is as if you have 1 by n into sine pi by 2 n divided by pi, right? And sine pi by n by 2 will have a values of 0 or 1, the magnitude of this, right? I'm just talking about the magnitude. So say taking the magnitude, will have always either 1 or. So it's as if it mimics that, and you recall that 1 by n, the sum of this sequence this or the series, right, of say summation 1 by n is equal to 1 to infinity. This is divergent, as we know from our calculus, and because of which the series is also here kind of divergent in nature, right? And the third property was about and the third property was about rationality of the problem. Right? The third property was about rationality. The ideal factor filter is irrational. Right? In the sense that, and it implies that it cannot be realized since you know that in what we call as irrational numbers are those numbers in which you cannot express it in terms of the fraction p by q, where both p and q are integers, right? So likewise, in this case, the ideal filter is irrational, implies that it cannot be realized using finite resources, such as finite number of adders, multipliers, and delays. So that is what it is. So with this, what we will do is I will just stop sharing these notes, and we'll somewhat look at some of the computational parts that we had planned to discuss today. Let me stop. Let me share the screen. Okay. So let's discuss about some of the things that we have that we were talking about in the previous sessions. So last time we had discussed about the Haar wavelet, Haar transforms, and I believe I was following these online open access tutorials by MATLAB. So we had visualized Haar wavelet and also did some analysis about this signal approximations. We had matched the sleeping rate with heartbeat rate of a baby child and look at the correlation. So, so here we see that it can even be used to say for digital watermarking as it's seen here. So watermarking is an important data protection tool, and it's a passive protection technique where a marker is covertly inserted in order to verify the authenticity or integrity of the data. Wavelet technique in general and the hard transfer in particular are frequently employed in watermarking images. And this example illustrates the use of Haar wavelet in watermarking an image and recovering the watermark. The example implies a simple watermarking scheme chosen for the ease of illustration. In this scheme, the watermark is inserted in the approximation coefficients at level 3, right? And you have, say, you have an image of a mandrill with one of a honey badger, and and so you have this mandrill image. You read it using this I'm read function. Then you convert into grayscale image, and then you resize it in this by the into the in this 2048 cross 2048 number of pixels, and then you just can just show the image. So this is the command for it, image sc, and you can have the color map in terms of gray. Of course, title and the rest are obvious. So here what it was done is, say we obtain the hard transform of the mandrill image down to level 3. And we recall that Haar wavelet is a, so first of all, we have to prescribe to the extent to the level of approximation that we would want to. And I believe this thing was discussed in the demonstration in the week 4 course, and that's what you see here. So you obtain in terms of say 4 matrices, right? And the first matrices, as we know, it's contains the most approximated image LL version, right? So LL is the low pass filter, and you are applying it twice. So it is, and going further into this, right? So this gives us the first I mean the approximate image, and the likewise this gives us the horizontal version, the horizontal edges, and HL gives us the vertical edges, and the H gives us the horizontal diagonal edges, right? So that is what they imply. And here only the first, this one was is plotted, and it's, you see that it very much resembles the original picture, right? And what you can do is, then we want it to, we are reading some other image called honey badger and storing in this variable called watermark. And then of course we are extending it again in terms of, we are just converting the image into double format, into double what do you call, number format, and we are resizing it to 2 cross 4 8 cross 2 cross 4 8 pixels. Then we are performing a Haar wavelet of Haar transform of the image again to level 3, and we see that this is how it is, right? And so now what we do is we can add the honey badger watermark to the mandrill image by attenuating the level 3 approximation function of the watermark and inserting the attenuated coefficient into level 3 mandrel approximation coefficients. So we have LL watermarked, which is this part, LL watermarked version, right? And we are reducing its amplitude, as we see here, LL oil plus each one, right? Right. So we are just watermarking. So we are uh, have taking the original image of this of the mandrel and adding an attenuated version of the watermark, because we are multiplying it to pi minus 4, then pi to pi 10 pi minus 4, and then we perform this I Haar 2, which is the inverse Haar wavelet or Haar transform in 2 dimensions, providing all these providing a new coefficients for the approximated image coefficients, right? And then we see this is how the image looks like. So it's mainly for protection. Of course, it won't be visible because we have drastically reduced the attenuation. However, it seems that um, you can recover the watermark using the Haar transform. So all that you have to do is you have to do the Haar wavelet transform of this, or the Haar transform of this, to a level number 3 and get it back, right? So it's like you are reversing the process. And you see, I have the image of this honey badger here, right? So was one example where you clearly saw how things can. It's only a person who has actually modified it will be knowing about how to. Uh, and that person will only know about uh, how to get back the image. And ensure whether the data the integrity of the data is intact or not. So that is one such example. And rest, of course, you can take a look at all this MATLAB documentation and say, uh, and it has quite a bit of resources to deal with and to be able to use it for your own purpose, right? So that was some of the MATLAB aspects that we had to talk about. Of course, we'll talk it further as we learned that in lecture number 5, or in the week 5 of this course, you'll be dealing furthermore into the wavelet transforms. So, so today I believe it's the right time to start talking about PyWavelets, the package which I had mentioned in the first tutorial of this session, session series. So this is the that I was talking about, PyWavelets, right? So it's an open source wavelet transform software for Python, and it combines a simple high-level interface with low-level C and Python performance. So the way you would use it is that PyWavelets is very easy to use and get started with. So as you see that we can just import PyWT. So PyWT is the package, and you recall that Haar wavelet is a special case of debaucherous wavelets. Now, let's just take a look at what they mean, right? So, what is debaucherous wavelets? Of course, I'm typing it in a random fashion, and let's get the Wikipedia link. So, this is the Wikipedia link here. Right. Now, debaucherous wavelets are based on the work of Ingrid Debaucherous, and they are a family of orthogonal wavelets which define a discrete wavelet transform and are characterized by a maximal number of vanishing moments for some given support. Right? And with each wavelet type of the class, there is a scaling function called the father wavelet, which generates an orthogonal multi-resolution analysis. So this is how it looks like in 2D, and it's a case for wavelet type 20. And so say this is different. So you have the scaling function, and you have this wavelet function. And if you know from the definition of of a wavelet function that the mean always has to be 0. And that's the reason what you will see is the area above the curve is the same as the area below this, or y is below this, below this horizontal line, right? So however, for scaling function, there is no such requirement. And that's the reason you see the area above this vertical line is greater than the area under the vertical line. So which means, of course, that they do not, so the area above the line is positive area, below the line is negative area. So since positive is much larger than the lower, the negative one, so effectively you have positive area. However, for a wavelet function, you have that this area is positive, this is also positive, and this is equally cancelled by the negative areas, right? And these are some of the wavelets. This is how we construct. Of course, we may talk about based on in the next. And what you see is the special case is Haar wavelet, right? And the softwares like you can support basing in possible in this case. Coming back to PyWavelets. So this is how we can. So this is how you're able to get the wavelets, get the wavelets, get the coefficients and all. And we can use it for image processing, as you see. See, right? You see titles are first of all, we will import the image, right? Load image. LL is the horizontal approximation, and LH is the horizontal detail, and HL is the vertical detail, and LHH is the diagonal detail. Right? And you could just plot this in this form. You see, so neatly you can do it. And here, uh, which we have used so for 2D wavelet of some different type, Bayer wavelet, right? You can just plot it. So some of the features of PyWavelets package that you can do 1D, 2D, and ND forward and inverse discrete wavelet transform. Here we can also perform multi-level DWT and either DWT. We can also perform stationary wavelet transform, the undecimated version of it. And we have this 1D and 2D wavelet packet decomposition and reconstruction. And we can compute approximations of wavelets and scaling functions and several such features. And as you see, the results are compatible with MATLAB wavelet toolbox. Now let's go and see how do we use it fundamentally, right, in a more nicer manner. Say about installation part, it's very easy. All that you have to do is first you have to get Anaconda package and then install it. So I have Anaconda say here. So this is an Anaconda that I have on my system, and the way we have to do is in Conda installed PyWavelets. That's what we have to run. So let me run this. Right, so I can run it Anaconda PowerShell prompt. Let's install this. Uh, let me check whether it's it does it has it is it pre-installed or have I installed it before? So Py and what is so PyWavelets, right? See, it seems it was not installed before, so it's getting installed. Okay, so I have to move forward. It will be installing certain packages. See, okay, it's quite swift. Yeah, it's done. Okay, it says that does not have write permission to the target environment. Okay, so all that I need to do is rerun with administrator permission. Close this, open this again. We copy this and we'll directly paste it here. Run it again. Right. Right. So it was yeah, I just want to check what are the packages that are installed. What all environments do I have in this system? So Conda will be list, I see. So I have PyTorch, Phoenix, I think these are some of the ones installed here. Okay, fine. Okay, coming back. Now I can go back to Anaconda and open this console, and let's do some programming today. It is seems to be very let's increase the font size. Check where does it. This part is done. Of course, I can also use Anaconda terminal, Anaconda PowerShell prompt, and type IPython. This is how it looks. Right? And let's get going. So we have all that is done. API reference, we'll just go for user examples. So say import of PyWT. And of course, this is just too good. And I would better like it to save these results, right? So let me launch this VS Code. And sorry, I have to import PWYT. And let's Python environment base. Get executed. Now let's see what all wavelet families does it have. I can just close this MATLAB as of now. And then say we have imported this. Let's see what all families it has. So it has these many families: debauches, Haar, PyWavelets, and other such wavelets. Even modelet wavelets we have. Bio wavelet also is there, and we can get this. So this was the PyWavelet families of wavelet families that we have in PyWavelet package, and we can also list uh, to obtain the list of wavelet names in each family. Right? So let's try to get this as well. Shift enter. So Haar family has just Haar. Debauches family has this many types of wavelets, as you can see. Likewise, Quafflets, Bior, Morlet. So these are some of the wavelets here. And I can just save this file in the wavelets pack. I'll just put it here so that it's accessible to every one of you. So I'll just call this as using PyWavelets package, using PyWavelets package. Right, so this is done. Now let's move forward and let's create a PyWT wavelet of, it says debauches, but uh, let's start with the simplest case. So I'll call it Haar, and let's enter it. Right, so and let's print out its. Right, and then run it again. Yeah, Haar is there. Let's print the details. Print the details in. It's Haar. Filter length is 2. Orthogonality, of course, bi-orthogonal also, and it's also it's asymmetric. You know very well why, because it has a value of +1 in the range 0 to half, and then -1 from half to 1. And discrete is possible. Continuous is not possible, right? And there are some of the properties, as you know very well from all this. We can also create custom wavelets. Right? You can have all this. Of course, it won't be. Does it plot it? No, of course it not. So I just want to know, how do we plot these wavelet packets? Let's directly go to wavelet packets and see how do we plot it, because we are essentially very much interested in plotting. So all that we can say is ask plotting wavelets in PyWavelets package. Okay, this is how I plot. I see. So wavelet is equal to Okay, wave fun. I see. So this is what we have to do. Level is equal to 1. As call it 11 is equal to 1. Run it. So it's not wavelet. We'll just have to call W because that's what we have defined. Control enter. Okay, it's giving us quite a. Let's plot it. So this is how it looks, right? Of course, it's not properly Haar wavelet, but still, let's see how does file look. Why this is what it has been implemented here. Let's see. Let's look at some logs. I see it's not publicly accessible without subscription. So I'll just use this. This is a very nice resource, it seems. So I'll just create one new. So I'll say that resource. First markdown version. So this is the resource. When you run it, this is how you get. We can of course edit it. Simple signal analysis is using discrete wavelet transfer. Here's the resource. I'll just copy these codes so that it's all in one place. Right, and we'll just generate all this and try to understand from here itself what is trying to be matplotlib and PyWavelets. Then we generate the signal by discretizing from 0 to 1 into 1,000 discrete points, and we do not take the endpoint. So, and then get the signal which is cosine 2 pi into 70. So it's like 14 pi t plus sine 626 pi t. Then we apply dw to discrete wavelet transform this using Debauche's wavelet of first the coefficients. Then we plot it and look at the signal, original signal. And what we do is also plot all these coefficients and get it. And let's see how it looks fundamentally. So this is how it is. Approximation coefficients are like this. CA, and these are the detailed coefficients. And general the approximation general trend of the signal, while the detailed profile insights are high frequency components. Seems like a nice resource. I would highly recommend going through it. And this is what we are analyzed in the main page, this PyWavelets package. So that's it. So essentially, I believe with this, we end our tutorial today's session. And I think we got introduced to a lot many things. And in the next session, we will start dealing with, let me stop sharing. So in the next session, we will start dealing with some of these ideas, and furthermore try to understand how the software of these packages work by some examples. And I believe that's it. Yeah. Okay. So I'll just close this session for today. Bye.